For this part of the module, 2.4 Chemical Reactions and Energy, we'll be focusing on this objective: the use of bond energy data to calculate overall energy change for a reaction and to identify whether it is exothermic or endothermic. First, I will introduce some key terms and concepts. If a reaction is endothermic, it will take in energy. A nice way of remembering this is the starting prefix En tells us the energy is entering. If a reaction is exothermic, energy will be lost. We can remember this by the prefix Ex, suggesting the word exit. We are using bond energies to determine if the reaction is endo or exothermic. So the term bond energy refers to the amount of energy needed to break 1 mole of a particular bond. We can calculate the change in energy by adding the bond broken or bonds of the reactants minus the addition of all the new bonds formed or the bonds of the products. If we get a positive result, the reaction will be endothermic as energy is gained, and if the result is negative, the reaction will be exothermic as energy is lost. The number calculated is the magnitude, the amount of energy lost or gained. We are always given a table of bond energies when working out these questions, and my tip is to always draw out all the bonds of the reactants and products and cross off the bonds when accounted for to make calculating the energy change easier. I will go through a worked example using the reaction of the decomposition of hydrogen bromide. This reaction is written as 2HBr makes H2 plus Br2. We are given the bond energies for the bonds used in this reaction. Then we should draw out the bonds in the reaction, not forgetting we have 2 HBr molecules, and we should write down the equation for energy change. Now we are ready to calculate the energy change of this reaction. We need 2 times the HBr bond energy, 366, minus the total of one of the H2 bonds, 436, added to one of the Br2 bonds, 193. We can simplify that to 732 minus 629, which we can then calculate to equal positive 103 kilojoules. As the result is positive and the energy in is greater than the energy out, the reaction is endothermic. Now I will go through a foundation past paper question taken from the WJEC exam board. The question is, use the bond energy values to calculate the energy released when all the bonds in the carbon dioxide and water molecules are formed. And again, we are given the table of bond energies and the reaction with all the bonds already drawn out. As the question says formed, we are only interested in the bonds of the products. We have 2 double carbon-oxygen bonds with the value 805 as highlighted here in purple. So we have 2 multiplied by 805 for the carbon dioxide. Now we have 2 water molecules with a total of 4 oxygen-hydrogen bonds, each of these with the value of 464 as shown here in green. So 2 multiplied by 805 plus 4 multiplied by 464 equals 3,466 kilojoules of energy released when the bonds were formed. The next part of the question says the energy needed to break all the bonds in methane and oxygen molecules is 2,600 kilojoules. Calculate overall energy change for this reaction and use this value to explain why the reaction is exothermic. For this, we'll need our energy change equation. We are given the energy needed to break the bonds in the question, here highlighted in pink, 2,648 kilojoules, minus this from the energy to form the bonds, which we worked out in the first part of the question, highlighted here in orange, 3,466 kilojoules. This should equal negative 818 kilojoules. Therefore, this shows the reaction is exothermic as the result is negative and the energy out is greater than the energy in. Finally, I'll work through a higher pass paper question taken from the WJEC exam board. The question is, the equation shows the bonds which are broken and the bonds which are formed in the production of sulfur trioxide. The bond energy of a sulfur-oxygen double bond is 523 kilojoules. The total energy needed to break the bonds in the reactants is 2,587 kilojoules. Calculate the energy needed to break an oxygen-oxygen double bond. As we are given the energy to break all the bonds, we only need to look at the reactants. There are 2 sulfur dioxide molecules with a total of 4 sulfur-oxygen double bonds. We are given the bond energy of the sulfur-oxygen double bond, highlighted here in blue, 523 kilojoules. So this multiplied by 4 plus the unknown oxygen-oxygen double bond should equal to the total energy needed to break the bonds, given in pink, 2,587 kilojoules. If we simplify the equation, then rearrange, taking away 2,092 kilojoules from 2,587 kilojoules, we should get 495 kilojoules, the bond energy for the oxygen-oxygen double bond. The last part of the question is, calculate the overall energy change for the reaction. And again, we need to use the energy change equation. The energy change for the bonds broken was given in pink, 2,587 kilojoules. This minus the 6 sulfur oxygen bonds, each being 523, should equal negative 551 kilojoules. This shows the reaction is exothermic as the energy out is greater than the energy in.